Columbia University. String theory consists of tiny little strings like a rubber band. Each vibration of the rubber band corresponds to a subatomic particle. And that's why we have thousands of these subatomic particles. They're not particles at all. They're nothing but musical notes on a tiny vibrating string. Recently, however, there's something called M theory being proposed, M for membranes. That's defined in 11 dimensions, and it includes all of string theory. This means that perhaps our universe can now be viewed as a gigantic bubble membrane of some sort, floating in a 11-dimensional hyperspace, and that raises the question, are there other bubble universes out there? And Dr. Randall of Harvard University says yes. Dr. Lisa Randall is the author of the book Warp Passages, and she's an expert on M theory. And so with Dr. Lisa Randall, we'll talk about this new theory called M theory. The first question for you, Dr. Randall, is where did you grow up, and how did you first get interested in something as abstract as theoretical physics?
Hi. I grew up in Queens, in New York. I guess I didn't start off interested in physics, per se. I like science, but really, when I was a kid, I liked doing math. I think a lot of people have some specific moment or specific teacher that they point to when they say why they became a scientist. But for me, I think it was just the fact that I really did like doing math. I actually very much liked the fact that there were answers, that you knew whether you were right or wrong, and that it wasn't just a matter of opinion. And I don't know if that was because, early 60s were a time of upheaval or whatever, but I really liked the fact that there were definite answers to things.
And was there a particular book, like in Einstein's early history, there was a geometry book that fascinated him?
Yeah.
Was there any thing like that?
I know, it sounds kind of bad, but I really can't think of one specific thing. I think basically I just enjoyed doing it, and I didn't even always have great teachers, but I did have, a couple of good teachers, along the way in junior high school or high school. By the time I got to high school, I really did start getting interested in physics. That's the first time I had a physics class, and we had it in 10th grade, so sophomore year. So by then, I didn't actually know before then that I actually wanted to do science, but at that time, I began to think about it a lot more seriously.
Okay, and what was the transition between math and physics? We've had mathematicians on the program who talk about the internal beauty of mathematics, but physics is quite different in the sense we're talking about the physical universe. So what was the transition between math and physics?
Well, ironically, one of the things that is kind of fun in physics is all the things that you don't know the answers to. So there's all these... although I didn't start off from that direction, I think as I've done physics more, I've gone more and more to appreciate just how many things there are we don't understand and how many things would be very nice to explain. But in terms of what you actually do, I guess I did want to do something that was more applied to the world. Although I enjoyed math quite a lot, I did want to do something where there was some connection to our physical universe.
And theoretical high-energy physics is perhaps the most abstract and the most mathematical of the branches of physics. What led you in that direction?
Well, I guess one of the things I did is I actually really liked model building. So what model building is sort of trying to get beyond, say, what we know from experiments, standard model, but sort of do it more incrementally in some ways. But it involves putting together more or less known ingredients, more or less known physical ingredients. What are the forces, how they act? But trying to go a step further and sort of put them together in a more comprehensive fashion so that we can understand things that we haven't yet understood, like where math comes from, for example. So I think I just enjoyed actually just playing those games in the beginning. And then as I learned more, then I got more into the sort of more formal mathematical aspects of it.
And also, did you have any experience being a woman? If you take a look
I had a lot of experience being a woman.
Right. Any negative experiences, I apologize. If you take a look at any physics conference, basically you see a whole ocean of male figures. How did you feel being a woman in the field of high-energy physics?
It's a funny thing. I think that it's something that I became much more conscious of, actually, in the later stages. I think earlier, certainly in the very beginning, when we were just doing math or whatever, there was no question who was getting more correct answers. I mean, that was one of the things that was nice. You couldn't say someone was bad in math if they were getting a better score than you were. So I don't think it was considered that strange. I just was doing what I did. I might have been oblivious, but at the time it just seemed kind of normal. I just was one of the people who did that. As I got into the field, and of course, it's not to say that I didn't notice that there weren't that many women. And certainly by the time I was in college, it was disappointing how few women there were in my classes or that continued with it. And, in retrospect, I realized how it could have been a lot easier if there were more there. But I don't think I didn't recognize it at the time. I think students today actually are much more conscious of how much it does affect their experience. I think I wasn't really fully cognizant of it. I just was doing what I did. I think later on, though, as you get to more advanced stages, oddly enough, it becomes more obvious and has more effect. I think then I felt it more.
But there was no problem with promotion or getting recognition. You felt you were treated fairly by the physics community?
Well, I wouldn't say everything is fair. I mean, I do think there are problems. I think I did well, and so I really can't complain. But I think things might have been easier in certain circumstances. In fact, there certainly would have been easier in certain times. It's really not perfect, and I mean, I just think that it does affect your experience. It can be an advantage. I mean, one advantage is that when you go to a conference, people do remember you. So early on, before anyone knows who you are, that's probably an advantage. But I think there's a lot of ways it works against you too. And they're subtle. It's not a big thing. And certainly, overall things, some things work out. But I don't think things are actually completely fair yet.
Okay, now let's talk about physics, specifically the four fundamental forces, including gravity, which is perhaps the strangest of the four fundamental forces. So could you elaborate about the four fundamental forces and why gravity is rather different?
So the four forces that we now know about are electromagnetism, which most people have heard of. And there's also two other forces called the weak and strong forces that were discovered much more recently. The latter half of the last century. And we'll talk about those shortly. Those have to do with nuclear interactions, for example, or what holds together a proton. But then there's another force, which is gravity, which, of course, also was known for a long time. But gravity really does seem to be very different than the other forces. And one reason that it's different is just that it's so extraordinarily weak. If you just look at what the masses of particles are, or just what we know about particles, it seems that it's actually inconsistent for gravity to be as weak as it is. The scale is just many orders of magnitude. The mass scale, if you were to associate a mass scale with gravity, it's many orders of magnitude, about 16 orders of magnitude higher than the other masses that we know about in particle physics. And 16 orders of magnitude is something we certainly like to understand. It's just so weak, we really don't know what's going on there. Also, if you extrapolate the three other known forces, aside from gravity, to high energy, it does look like there's some sort of unification. Now, which theory you have determines exactly how precisely unification happens, but it does look like at high energy, the forces were at least of roughly comparable strength. And again, gravity just stands out because it's just different. It doesn't seem to exactly unify with the other forces.
Well, we're running out of time. However, when we get back to the second part of exploration, I'd like to ask you about Einstein, because it was Einstein who had this dream, a dream to create a theory of everything, a theory that which would contain gravity, the electromagnetic force, or light, and even the quantum theory of matter. And Einstein thought that it would allow him to, quote, read the mind of God. So after the break, I'll ask you about Einstein's quest for a theory of everything. Now, Einstein tried to unite gravity with light, with electromagnetism, and that approach, unfortunately didn't work. However, recently, in the last several decades, there's been a lot of work, especially with Steve Weinberg, who was on this program a few months ago, concerning unifying some of these forces. So could you explain some of the progress that we've made since the 60s and 70s concerning unifying some of these quantum forces?
Sure. So one thing is when we look at the various forces, say the weak interactions, strong interactions, and electromagnetism, At the energies that we tend to see things, the energies we experience, they appear to be very different forces. We know electromagnetism gives rise to a long-range force, whereas we know about the weak interactions. The weak interactions, for example, lead to nuclear decay. That's one of the places they occur. It also occurs in the sun. But it's a very short-range force. It really seems quite different. And also strong interactions seem extraordinarily different because they're, in fact, so strong that you can't even isolate the particles that carry the strong force. So, ironically, one of the reasons we didn't see the strong force was because it's so strong that we don't see charged objects that are charged under the strong force. Now, this is all true at low energy, but when we go to higher energies, the forces begin to look more similar. And if you go to energies around 100, I measure in GeV, so about the mass of the W or the Z, which is about 100 times heavier than the proton mass, the forces are beginning to look more similar there. They still don't have exactly the same strength, but they all seem to be qualitatively the same. They sort of all look like they mediate fairly long-range force on that scale. But then you can extrapolate to even higher energies. And I should say we actually know a precise procedure for finding out how interactions depend on distance or energy. And if we went ahead and extrapolate to higher energy, we find that in the standard model, all the forces have roughly the same strength. But if you actually go to extensions of the standard model, and we'll talk later about why we might believe there is more to physics than the standard model. And by the standard model, I mean the standard model of particle physics that includes three forces and the known quarks and leptons which interact under these forces. But if we extrapolate to high energy, it looks like the forces can have the same strength, especially in extensions of the standard model. So that does seem to be huge progress in terms of forces being unified, because it really does look like at high energy. These three forces might have the same strength, which means that perhaps they're all manifestations of a single force above that energy.
Okay, now Einstein spent the last 30 years of his life chasing after a, quote, theory of everything. He wanted a theory of gravity, light, and also the quantum theory in his later years, and he failed. However, today we do have something called string theory, which is the leading candidate, in fact, is the only candidate for a theory of all fundamental forces. So tell us a little bit about string theory.
So, although I mentioned the fact that gravity looks different because it's weak, there's another problem with gravity that I didn't mention, which is just that we don't really know completely how to make a quantum theory of gravity, at least certainly not without string theory. It looks like when you try to make a theory that has both quantum mechanics and general relativity in it, you just run into trouble at short distance, for example, because at low energies we usually don't notice this problem because you either are in a domain where either gravity is important or you're in a domain where quantum mechanics is important. And if one is small compared to the other, we don't have to worry about it. But if you go to a regime where both are important, we don't have a theory that certainly the theory without string theory doesn't work. It just seems that both forces are trying to do their thing and they're just incompatible. However, if you have string theory, if you, instead of assuming, like we do in particle physics, that the fundamental objects are particles, which is to say point-like objects, if you assume the fundamental objects are strings, which is to say slightly extended objects that look like strings, it seems that these problems can be ameliorated. We don't completely know how to combine quantum mechanics and gravity because we don't completely know how string theory really works. But it does look like it's a theory that can consistently contain both quantum mechanics and gravity. Of course, it really does that in a theory with many more dimensions of space than we have, 10 or even 11 total dimensions, which is to say 9 or 10 spatial dimensions. So it's certainly gravity, but it's not naively the gravity we expect. And so there are many challenges that still remain, although it does look like it's a theory with both quantum mechanics and gravity. We want to make sure it's gravity as we know it, which means we'd like to understand how we have three spatial dimensions, for one thing. And also we'd like to see it solve some of the problems that a theory that has both quantum mechanics and gravity is supposed to solve. And we still have a long way to go in really fully understanding all of string theory's implications.
Okay. Well, it was almost 30 years ago when string theory was shown to be consistent only in 10-dimensional